Welcome to the Haskell Meetup. It's great to have here every month. We're only going to have one talk tonight, which is going to be Trevor from Base. He's going to be talking to us about Heap profiling and fixing performance leaks in Haskell programs. After that, what I thought we'd do is, it's been about 6 months since we started the group. And so we just have a little time for discussion and feedback, things that people have enjoyed so far, things that people would like to see talks on in the future. Hopefully that in turn will inspire people to come forward and volunteer for talks on these things and so on, but just like where it's been and what people would maybe like to see out of it so that we can all have some sort of communal discussion on that and come out with some good ideas. So yeah, take it away, Trevor.
Thank you. All right, so as introduced, I will be giving a talk on heap profiling and that's right, and debugging space leaks in Haskell programs with a special focus on evaluation and laziness. So it's possible to get really theoretical and formal in this kind of discussion and get into the organizational semantics of Haskell and the formal grammar, and I'm not going to do that. I'm going to work through really concrete and easy to relate to examples to kind of motivate the idea of debugging space leaks in Haskell programs. So first, what I'm going to do is I'm going to kind of give a refresher course on evaluation in Haskell and in general in non-strict environments. And then with that sort of example, I'm going to move on to a concrete example of debugging a non-toy but still manageably sized program which fits on slides, or at least the interesting parts do. And work through debugging a couple of space leaks and that, some of them due to laziness. So, in theory, it's very simple to capture all the principles that govern Haskell evaluation and its non-strict semantics. And I could write a very small number of mathematical symbols to describe all of that in a way that I would not be able to understand. So instead, what I'm going to do is give a really concrete example and work through something which showcases Haskell's laziness. And if you want, if you're interested in the nitty-gritty of it and a more formal treatment of it, then you can check out the Haskell Wiki, which has a good article. Graph reduction is sort of medium difficulty, and the data digital semantics article is a little bit trickier, but really clever. So Haskell's values and expressions and everything are non-strict, which means that unlike in a language like OCaml or Python or Java, it's not called by value. When you call a function, you don't pass it the values onto the stack or whatever when you call a function. Instead, the values themselves are not computed until they're actually used, which means, and actually needed means that either it's forced by a particular I/O primitive, or the runtime needs to make a decision based on that value, meaning pattern matching, such as a case statement, or the equation syntax, or an if statement, which all in the sort of internal language of GHC, for example, boils down to effectively a case statement. So, looking at an expression and saying which one of these is it, that's when the evaluation happens. Now, in Haskell, it doesn't happen unless main asks for it. And so everything that gets bound into main happens, everything that does not get bound into main does not happen. So if you're writing a library, or if you're talking about a part of a program, it's more interesting to talk about strictness and evaluation as a relationship, i.e. if my function is evaluated, then which of its arguments is instructed, rather than speaking in absolute terms, because of course if that function is never referred to by main, then it never gets called, and it never happens. And furthermore, you can then reason about it as an argument to other functions, etc. So as a very, very small example, imagine a list XS, and the strictness of this case statement with respect to excess. Now, it does care about whether it's a empty list or a concept. And as a consequence, it is exactly that strict. If this excess could be undefined, i.e. the value which when evaluated crashes the program, cons to undefined. But it would still return true in this case. That would evaluate true when forced, even if it was undefined, cons undefined. So that is to say that it's not strict in the head or the tail of excess, such that only the outer cell, or the lists or linked lists in Haskell, is ever evaluated. So this could be, some form of code data, like an infinite list or something, and that would still converge and give you a regular, good old-fashioned true. So when I say outer con cell, what I'm referring to is talked about in the literature as something called weak head or WHNF. And there's a lot of talk of things like reducible expressions and whatnot. I'm going to give it a little more hand-wavy of a treatment and talk about outermost constructor. You can sort of think of reduction working that way. Whenever I say force or I say evaluate, what I mean is taking an expression and computing until I get the outermost constructor. So in this case, that would just be whether it's the empty list or a concept. I don't look inside of that. So, as I said, Haskell is non-strict, and GHC, like other Haskell implementations, implement non-strictness with a combination of laziness and sharing. Laziness really means that the non-strictness is implemented by, rather than strictly evaluating an expression, having a thunk data structure which points to the code you need to get that value, as well as the environment of the variables that it refers to, so that you can later eventually yield that value. Or non-value in the case of divergence, i.e. not terminating. Sharing means that expressions are evaluated once per name. So if I find something with a where clause or let or top level or as a parameter to a function, then it only gets evaluated once in that way. So for example, if I were to square a very complicated to produce number, then that complicated to produce-ness would only happen once. So in this program, to get the 10,000th Fibonacci number and square it, I have to only do all that Fibonacci computation one time, and then I can produce the square of that number with just times. Let's walk through a little less trivial but still fairly simple example that really showcases how non-strictness relates to the semantics of the program. Now, here we have the expression and repeat false, which really means repeat takes its argument and gives you a list of that infinitely many times. So false, cons, false, cons, false, cons, false. And takes a list and ands together each of the Boolean arguments, or for empty list gives you true. So this is going to give us false. So let's think through the runtime and say, okay, how do we get to the false given and repeat false? So as I said, GHC implements this with laziness, and I'm going to be a little bit loose in laziness versus non-strictness. Non-strictness is what the Haskell report says, and it's sort of the technical term. And laziness is the implementation strategy along with sharing that gives us that non-strict semantics. Like any Haskell expression ever, and repeat false starts out as a thunk, which when evaluated, gives us ultimately false, but unpacks the and first. But note that if it was never referred to, or for whatever reason wasn't forced, it would just stay as a thunk, right? Beyond, if it wasn't forced beyond. So let's break it down, and the first step is to consult what and is. Now I'm using a little representation that I invented, which just put it in angle brackets, and I just kind of express the code that you would need to resolve that conflict with force. And I'm being a little bit sloppy because in this case, false itself would be another thunk which when forced would return false. But let's consult the definition of and. So what we had before was and this func, which gives us repeat false. Now, substituting in this func for xs, which is the first rewrite rule to get us to that eventual false value, gives us case this func of the empty list for assigning the two sides of the cons to head and tail respectively. Now, as I said before, evaluation doesn't happen until a decision needs to be made. And case is a great example of when a decision doesn't need to be made. So this is a pattern match. We must evaluate it. We have to force it one button, as always. So in order to do that, the func, which yields repeat false, we need to know what repeat means in order to get any further. So let's substitute in that definition to see what the next level is. And repeat gives us its argument infinite times in infinite list. So looking here, we get but we don't, when we force it one level as a singly linked list, we don't have to do infinitely many anything. Instead, we just get the very outermost constructor and then two funcs, which, when forced, will yield the next stage of the computation. So, as should be obvious, the second category is not an empty list. It's the func false and the func which, when yielded, gives us repeat false as the tail. So, substituting that in to the definition, to the case alternative here, replacing H and T with their respective arguments, we get this func which yields false, and then the and operator, and then that func which returns and the tail, the func return, which when forced gives us repeat false. All right, so as a final step, let's consult the definition of the and operator. And now, these aren't none of these are the definitions that find in the report or in base or anything, but rather semantically equivalent definitions that make it extremely clear what's going on, such that they all use case. They're usually defined using this equation syntax, but I'm not using that just to be consistent and always evaluating in this case construct. So you can see here that the definition of the and operator is absolutely strict in its first argument, i.e. you can't get anywhere unless you evaluate the x. Now, of course, operators are regular functions in Haskell that have symbols for names. So we can define them and use them in the text, but otherwise they're just normal functions. So substituting this definition into what we've got so far, this func false and the func with the and repeat false, will give us case the first part of true, second part false false. Now the func which yields false when forced, of course, is false. So we match the second pattern, which is false. Now note here that this branch never is valued, this func and func repeat false. So the program does stop. We don't have to compute every false to find out the and of this repeat false thing is repeat false. So that was really just a very simple example to walk through the logic of the runtime, evaluating this non-strict expression, which still is very helpful in reasoning about what's happening when you encounter problems such as space links, which is the focus of the rest of the talk. And you can get a lot more info on this on the Haskell report and the Haskell wiki and Stack Overflow and the internet in general. All right, so my example here is an inverted index. So, and this is just a showcase of an example of a place where you can actually really run these programs, these problems, even in a not that small program, but while still being concrete and relatively. So an inverted index is really just a map, ultimately, from contents to documents, i.e. we're taking a bunch of documents, we're indexing them, and we're mapping the words from each document back to that document. In particular, we're building a record level inverted index, so we're discarding like location information or phrases or sentences or anything like that. And this is, just to give you a little foreshadowing here, laziness is going to be problematic for us. So an inverted index is very simply a map from the contents. In this case, we're going to simplify to say the words back to the documents that the words occurred. And then we want to implement the ability to query that index and find out, given a particular word, what documents it occurred in, or given a query with multiple terms, which documents all of those occurred in. So that's an and query. Now I'm going to walk through the implementation of the really core aspects of that. And we're going to see where the naive implementation of that brings us performance-wise. So we're going to make a really easy, obvious stab with what Haskell just gives us out of the box to attempt to make this inverted index. Now, the way we're going to represent this is, let's use strings, the sort of out-of-the-box character string type that Haskell gives us to represent our document contents as well as the terms that we're querying. So when I say the type term, which this is a type alias, when I say term, I mean either the search, the queried words themselves, or the equivalent type of the contents of the document. So I'm using terms. And now our index is, as promised, a map from those terms back to the set of the documents that those terms appear in. Now, let's not forget what that string is that Haskell gives us up the box. It's just a type alias for a list of characters. That is lazy, singly linked list of lazy characters with lazy pointers. It's all lazy. So, this is how we're going to create the index. Now, suppose we have an index document method that gives us a new index given an old index, the contents of the file, as well as the path to that file. So this create index method is really the top level entry point to building an index from the file system. We're given a list of the documents, the paths to the documents that we want to index, and we produce, i.e. we have an IO action which returns an index that's fully created, okay? So one approach that we could have taken is to make this a list of contents of, or a list of tuples of, path and contents to a pure index. But what I'd rather do is I'd rather have just one file in memory at a time. So I need to, what I want to do is I want to read a file, add to the index, throw away the contents of the file. Read a file, add it to the index, throw away the contents of the file. That's sort of the goal here. So that's a fold. That's a really straight, obvious fold, except that's a monadic fold. So that's given to us by fold then. Now that is, if you're not familiar with it, it's basically fold L, except there's a line after every set, giving into the accumulator. So we're folding with this accumulating function, and here is our empty index that we're starting from as the initial value of the accumulator, and the list of paths to the document that we're going to read. And our accumulating function here is given by the starting value of the index, term, which is the contents of the file in this case, and then an IO action, which produces the new version of the index. So in order to accomplish this, we have a very simple monadic function here, which reads in the file and then returns the index applied to that contents of that file and the path to that document. So index document is where we do the actual combining of the index with the new document. But this is the monadic fold part, that's pure. Index document part is pure, because we're returning it to get back to our IO index. All right, so let's consider what the index document function itself is. So as I go into fold in, it's just fold L. So now supposing the segment terms function, which breaks up the document contents into a list of terms, we have index document, which takes the old value of the index, the path to the document we want to add, the contents of that document, and gives us the next version of the index with that document added to it. So the way we do this is we first split up the document. So you read, when it's a bunch of dotted together composed functions, you want to read it from right to left. And so we're taking the segment terms function, which breaks up the contents of the file into a list of terms, which are strings for now. And we pass that value, that list of strings, to this map thing. And what that does is it considers each word and produces a tuple of that word in a set of just that document name. So we have this big long list of every word on the left and just the same right thing, which is a set containing just the path of that document. We slurp that up into a map, and that compresses it so that each term only occurs once. We don't see any duplicate terms. So I'm not filtering up stop words or anything here. So the is only going to happen once after this stage. And then I combine it with the existing index using union. Now I have to union twice because I'm unioning first the index, which is the map, and then for each value, I'm unioning the existing set of documents pointed to by that term with this one single term, or there's no corresponding. So now finally, for the indexing, let's consider what segmenting the terms means. Again, right or left. We filter out non-alpha characters, and we leave spaces so that we can split later. Then we lowercase everything just for normalization's sake, and split it up into words, and that gives us our list of terms in that document. Now, the last code component before we intend to run this is the querying component. So we want to be able to give an index, look up which documents all of those terms are in. So the way that this works is I am mapping over every word in the query and looking up a lowercase version of that term in the map, and the result of that is a list of all of the sets of documents that those terms occur in. So it looks at the first word in the query and then finds that in the map, and that gives you a set of the documents that word occurs in, etc. For each of that, and you get a list of sets. Now, intersections is a function which I wish was provided to you, but unfortunately isn't. I had to write it. It's very fairly obvious. It takes a list of sets and combines them together into a single set by intersecting it with the pairwise. And then what you result with here is the set of documents which every term occurs in. And then I just listify that with two lists just for interface's sake. All right, now that's everything code-wise. Let's run that on a couple hundred documents and see what we get. All right, pilot, run it. I'm doing that right now. Okay, that's not good. Open file. I didn't type open file anywhere, but somewhere in the covers was open files, and couldn't. There are too many open files. So I ran out of files somewhere. But where might I have been opening files? Well, I only really did an IO with read file here. Sorry, yeah, read file here. So it must be somewhere under read file. Let's consult the definition of that. Okay, here we are. Open file, great. That's the one that's failing. So if you look at this, it looks like on the left hand of this bind here, we should be opening the file. On the right hand, we should be reading the contents and closing it. So that's not happening, but that's what it looks like it should be happening. All right, time to read the documentation of HTML contents. Aha! Once once you pass the handle to HK contents, it's not open, it's not closed, it's semi-closed. And it's not closed until everything has been read. Which I thought I was doing, but anyway, we now are confronted with the challenge of lazy I.O. i.e., we're given a pure value, this string, which in the course of evaluation, not just of the outer, cons of that string, but at the very end, we finally encounter the last cell, the empty list at the very end of it, and that has an I.O. side effect. It closes the file. So I actually have to go and read the entire file in some pure way and force it to be evaluated, and then it will close the file. So that way, that will give me the opportunity to not crash with that file completely. So, how can we do this? One thing you could do is, just force that. Force not the outermost constructor, but absolutely every constructor, every con cell, always we get an empty list as returned by HGet contents in the form of read file. That way, HGet contents will say, all right, last thing, I see it, close. And no more semi-closed handles, no more resource exhausted, we'll be good to go. Now, how should we do this? Why don't we just preserve our interface of read file, which should be possible, and build it on top of read file. Now, I've introduced a new concept here. It is called seek, S-E-Q, in doing so. What this does is it computes the length of the contents, i.e. Goes and counts, all right, there's one on cell 2, and then finally gets the empty list, and then gives you an integer. And what seek does is it forces that outermost constructor, i.e. that integer, which, length was the heavy lifting, and doing all the other representation. And then I give you back the contents, wrap back a guide. So that was all well, but what is this seek thing? Well, how would you implement it? I thought, Trevor, you just said that everything was Haskell and Haskell was lazy. That you can't just magically force things. Well, actually, yeah, you can write a function. It's a primitive. Its contract is I evaluate the first thing you give me, one level as always, and I return the second thing. I.e., it evaluates to its second argument, but only after evaluating its first. And this blending notation here means that exactly what I just said. If you pass it an undefined value as its first argument, it's undefined, even though it doesn't use the value in its resulting expression. It is strict in its first argument. Not a function, you can't write this, it's primitive. So first we compute the length of the contents, get that integer, throw it out, and then we give you back the contents, thereby forcing HGet contents to close the file. All right, great. So now we should be reading a file at a time, throwing it away.
So it's length that's forcing the whole file to be read?
Yes, that's right. It has to, visit every node of the linked list to get that number. All right, so now we should be getting that memory usage that we were hoping for of, allocating the file and then adding it to the index, throwing a little bit, and then throwing it away, and then adding to the file, and all should be merry after this. Now that we can, deallocate our file. So let's run it, and I've just, passed it a couple of words that I expect to be a lot of documents, and what do we get? Well, it doesn't crash. That's good. It runs, but it's slow. And it's consumed some 2 gigabytes of memory. I thought that the inputs were only about 28 megabytes. I'm using Project Gutenberg books. Yeah, that's not right. What's wrong? Well, let's find out. Fortunately, we're using GHC, which is world-class software with world-class memory profiling. However, you can't use them yet unless you've got your stuff configured right. Which go home and do this. Go go to your log config file and add that line, library profiling is true, and then recompile everything, and then you'll be good. All right? Good. So now we type in our GHC command to recompile, and we add -prof and -fprof auto, which used to be called auto all. And this will enable us to see what we want to see, i.e. a story told to us by the runtime system of what's happening second by second and who's allocating what. Now, this is fortunately built in, and all we have to do is recompile everything and get it. And we do this by rerunning our original command with +RTS, which says, hey, runtime system, start paying attention to some arguments I'm going to give you, and then -HC to give us the cost center heap profile. And we didn't type in cost centers in our source code, so we use -fprof auto to manually annotate all of our bindings with cost centers and say, hey, runtime system, when you get here, this is what I call it. If I do any allocations, remember it's me. Okay. Aha. Now, for those of you who can't see the numbers, they're pretty scary, so it's good. You can't, because it allocated 7 gigs in the course of execution. And this is a good example. Yeah, this is a good example of a heap profile that you never want to see. But usually the kind that you do. The numbers here are, it peaks somewhere in 600, 700 megabytes. And this green area is what's allocated by read file. And this blue and black is what's allocated by segment terms in the index document. So what's happening here, if I were to jump into the mind of the runtime system, is I would be reading a bunch of files, all of them, in fact, and then slowly considering each one of them and adding them to the index as it grows over the course of 18 odd seconds. And yeah, you know, the colors they sort of map back to the cost centers that were annotated. And you do kind of have to do a little bit of mental bonding with the runtime system and thinking about, okay, well, this is what's happening now. And that was the sort of point of the evaluation sort of review at the beginning. As we saw in that graph, we're getting a lot of files read and then slowly deallocated, which is the exact opposite of what we wanted. We were hoping to deallocate each file after it was read in. If you've ever seen a Stack Overflow in Haskell as you're trying to build a program or whatever, you've read it, you know, you got a lot of any of those sort of crashes saying like I ran out of stack space or dumps or whatever. This is the exact same issue. What's happening is it's building up things, it's basically allocating a lot of memory, and then finally it's collapsing that with the computation in this very expensive nested file that you build up. So what we have, in short, is a strictness problem. We're not forcing those at the right time. Where were we hoping to force them? Well, in add document. And we thought, hey, I thought that here in this read file prime thing, we were forcing. Well, we were. We were forcing the file to be entirely consumed. And then we were folding it over with fold-m, which, you know, fold-l is not, fold-l itself is not strict. But fold-m is as strict as bind, and, you know, bind, at least for I/O, is strict in its first argument. You got to evaluate something to print it or whatever. And we are also using as our accumulator, as the index, a strict map. So when you evaluate the map, the strict map evaluates all of its values. So that shouldn't be the issue, right? However, return is lazy. That's the problem. This return is forced, but return doesn't force its argument, and that's almost never useful. But in this case, has given me an excuse to talk for a minutes. So let's revisit that and not pass it a lazy value. We just did this exercise a couple slides ago with C. All we have to do is get that pure value, force it, and then we can pass it to return, which for some unbeknownst to me reason is completely lazy. when we get to the fold down, it will force the return, and then, or it will force, this add document, which evaluates the index, which is script, and then it can finally pass it to return and accumulate that way. All right, that's much better.
Yeah.
We're allocating a file and adding it to the index, which grows a little. Allocating a file, big one. Deallocating it as we add to the index, etc. It's very spiky, but that was sort of the goal. The goal was to consume these huge files one by one and add them to the index bit by bit. However, there's a problem. I said this isn't a bigger corpus or anything. It's still the same 28 megabyte corpus, and it's allocating 900 megabytes up to 125, 130. That's the peak there. That's not good. That's an order of magnitude bad, approximately. We would hope that if you're writing, for example, C, we would get spikes of a couple megabytes, right? At least not great. But what can be done, right? We have the right strictness, we have the right asymptotic complexity. Everything seems peachy. Well, let's look at how we were representing things. Strings, as I said, are linked lists of characters, which is really cool for I don't know, lazy I/O. But we're not really doing that. We want something that's efficient and represented kind of in a not horrifically memory efficient way. And the reason that it's inefficient is because it's a linked list of characters. You've got a con cell, and you've got a thunk, and you've got another thunk, and you've got a character, and everything's lazy, which means another layer of indirection. It's like, this is not even half the story, actually, it's about a quarter. So, fortunately, we aren't the first people to ever discover this problem. Somebody real smart.
I was just going to say a further issue is the characters are 32 bits, and your file is probably UTF-8.
Yeah, right. So
it's using 4 times as much memory.
There's a lot of multipliers of deafness, you're right.
Well, yeah, string is not recommended string representation.
Yes, that's exactly. So, fortunately, Brian O'Sullivan was like, hey, let's do it the right way for the first time. Data.text, great. An efficient Unicode text type fits the bill. Very finely tuned, widely used, some 700 odd reverse dependencies on package. It's good. And it gives us this dense, UTF-8 array representation as if we were using Y characters or, if it was a Java string or something, which, is a lot better than this linked list of madness. So let's go back and add that in. Now, we made this type alias for a very convenient reason, namely that I can change the types in really one place. Now, our term, every time we said term before, which meant string, now it means text. And we don't need to that read file prime anything before, because, when they were writing text, they're like, yeah, this is the way you probably want to do it. If you're doing script I/O, you're doing script representation, so let's just give you that. So let's use it. And all we need to do is, belong in text.read file where we're using the read file prime. Wherever we're using those data.care methods before to operate on the, contents of those linked list cells, we can now defer to data.text to use its more efficient variants, which don't unpack and repack and do all this shuffling. It just operates on the underlying UTF-8, UTF-16 representation. Now, which the big differences here are we have to use text.filter because there's no built-in predicate like that. And then it gives us text.toLower, which gives us an array that's lowercase compared to the ones that we've given. And then text.words, which is, we give it a text array or text representation, and then it gives us a bunch of little text objects that correspond to the words, like words that are created. And then our lookup term has to change, of course, to use text.toLower instead of using map lower to lower. Cool. So now everything should be good, right? We're using real strings now, big boy strings. Text. Now we just debug it the same way. And we shouldn't see that 8, 10x multiplication on top of what we already had, right? That's asymptotic wrong. This looks more like the first of the stack, where it's growing like kind of monotonically. Yeah, let's not do that. So, however, if you look at the axis here, the values of the axis here, it's 60 megabytes, which is a lot better than the gazillion from before. And it only allocates about 500 megabytes over the course of execution. Still the same 28 megabyte data corpus, so that's still outrageous, but better. But why did this happen? Why are we now hanging on to just more? So it's not because of a laziness this time, because we're lazy. We're strict. We're pretty strict everywhere now. We're reading in a file and throwing it away, reading in a file and throwing it away. That's not what's happening, right? We're building the index piece by piece. As you can see, the big difference is that it's not this and then that. It's happening all at the same time. That's indicative of good strictness, right? But what is happening? Wait a minute. Segment terms is the big read, not read file. Segment terms is hanging on to everything. What was the segment terms? Well, we were hoping that text.words would break everything up, right? And give us these little tiny words that we could then say, oh, I've seen you a lot. I don't need to store you a million times. Oh, B. We don't need to store B a million times, do we? And then we can just throw in a big block that's fully duplicated and whatnot, and just let the GC do what it's good at. Wrong. What words does is given to us by data.text is the right thing in absolutely almost every case, every other case, which is giving us a very efficient compute, very efficient to have a lot of view on the original array. So if you were going to store that array anyway, you don't have to store it twice, right? It's good in like a lot of ways that don't apply here. So the issue is that it's what we want to do really is copy those little chunks into their own little array boxes or the text boxes that we can feed into the index and have store only one per word. So what we got to do? Well, he's a pretty smart guy, right? He thought of that. He gave us a copy function. And what it does is it doesn't share store with the original structure. All right, so segment terms are culprit from before. Let's just annotate it with text.copier. We have to map over it. We've got a list of terms before a list of text. So now we should not have that horrific, skyrocket in memory performance. Okay, and alas, or lo and behold, that is, we do have alas, I'm not going to talk more really. Now the one that's growing this way is the index, as we wanted. The files are the spikes and everything, and they're going down, and they're going to be allocated in all as well. And the index grows until the very end where it happens in the program is. So 22 megabytes isn't great, right? As a peak, and allocating 213 megabytes overall, that's not wonderful. But it's asymptotic. It's constant, and the spikes here are not that many times greater than the average document size. Right? We have the documents of 4 or 5 megabytes, and the spikes are 16. So anyhow, if we really wanted to micro-optify this, we could go and represent this instead of a map of text to strings representing the path of the document. We could give those documents numbers and integers and use the really dense int sets and int maps and all that stuff. But that's asymptotic the same. It's just a constant vector improvement. All right, that's it. This talk has been brought to you by my consulting outfit, called Base. We do massive consulting, and I will be posting
processing a list of data twice. And once you compute it, slang and then process it. I'm wondering if you could do that in one pass rather than two passes.
Oh, yeah, I mean, in principle, I could, write my own, HGET context or whatever that is the right level of strictness and doesn't do that, and, use the low level I don't do it, whatever. You're right, that's why when they wrote text, they did it right. Instead of doing it that way. But we know, of course, it's not hash problems.
I'm not sure if this makes sense, but do you think that one of the strict IO libraries like pipes or conduit or enumerator or whatever would have been applicable?
Those are indeed helpful in similar situations. However, what we're doing is actually just plain old strict. Those are for managing constant IO, in a situation where you want to be long-lived and manage, within a pipe-like fashion. But we're just, accumulating data structure strictly and then appropriately. So in other cases, yes.
In your particular situation, where was laziness actually helpful? Like, why not just deep sea everything?
Deep sea does repeat understand.
Okay. Well, why not force?
You can, did you talk about bank patterns at all?
I talked about Seek. I didn't
Okay.
everything.
Yes. Right, and which is what I'm saying, that without patterns.
Bank patterns is not deep sea.
Yeah, it's almost like we can.
Yeah, well, no, if you define your data type deductively, there are bank patterns everywhere. It's deductively, we can run the form, so it's essentially normal. So that's like one thing that you can do. There's some really good slides by Johan Tibble for high performance Haskell, and basically the pipeline is at least when the first line of defense when you're writing new data types in Haskell is by default, if you're just sort of naively just thinking of it as like normally, typically being in normal form, when you're writing a data type, add bang pattern annotations to all the parameters of your algebraic data types, and then selectively introduce laziness back when it gives you better fusion or compositionality.
Right, I guess that's what I'm wondering, where is laziness useful
In other programs.
Okay, all right.
There's
That's
actually
my question, I was wondering.
almost no laziness here, right? The map is lazy, the text is, the map is strict, the text is strict, and I made return strict, right? The fold is strict, everything effectively is strict, right? It's Haskell, so, that's good. But otherwise, I'm not really using laziness features in Haskell.
But your composition of meta.text, though, is that some laziness is going on there, right? There's stream fusion going on.
Stream fusion isn't laziness.
Right, but you're not creating the entire
Well,
thing.
yeah, but that's not laziness. That's you're doing repeat compositions on data structure without looking at the intermediate value between. So let's just consider some case of you're mapping f then g over some list or text or whatever.
Stream fusion in certain forms relies on laziness because if you were in a strict language, it wouldn't preserve semantics, it would change termination properties.
It does anyways, though.
Not as good. Depending on the type of fusion, sometimes it's sort of flaky. But
Yeah,
in general, laziness lets more things terminate, and that means that you preserve more properties when you perform fusion. So that there's a relationship.
Yeah, but the punchline is fusion is sort of a way of saying we're doing a sequence of operations and we're never actually using the intermediate value. So we may as well just do a function that's a composition of those two functions and do a single construction and skip the intermediate text construction or whatever.
Right, but to preserve semantics, laziness is important because there are many transformations that Haskell can do that you can't do in other languages, not just because of side effects, but because of strictness problems.
Yeah, so in a strict language, fusion might make more programs terminate.
Is there a simple example of that?
Uh,
Off the top of my head, there's probably I'm sure there's a million very
I
simple
can bring up
examples,
some
but I don't have
ideas.
one line.
But
It doesn't help.
But basically, it's just more, the semantic issue is that more programs terminate when that doesn't deserve the meaning. Or at least that's usually the concern. Although usually people are okay with things terminating. It's just, it makes it less, it breaks the formal model.
What Carter said.
So at some level is the moral of the presentation that like laziness and side effects don't play nicely very well?
Or to sum it up, is this a case of easy made hard?
No.
Like,
It's,
could you use pipes or something?
why?
I don't know.
No. Why, so I wanted to make it, no. But it's a case of Haskell being, really great in almost every situation except for this one, which is extremely annoying. And you need to have a couple of tools in your belt to really kind of get to the root of it. And, working through at that sort of the level of, okay, what forces what is helpful to kind of get that.
Had you known what other language would you have thought this would have been perfect?
Well, this is a very trivial problem in almost any language. But, I mean, it's not particularly hard in Haskell. But
Well, you did seem to jump through a lot of hoops.
I did, although some of them were admittedly for dramatic effect. For example, I would never have started with certain. But the text copy one is definitely interesting. Non-laziness sort of orthogonal concerns is definitely worth being aware of. But yeah, I mean, it's not really that hard of a problem. Questions?
Do you know off the top of your head, do you give like the actual space complexity of the string data type?
Yeah. You mean the overhead?
Yeah.
No, I don't know if you had it. Yeah, you know.
I remember something along the lines of 5 words per character, but I'm not 100% certain.
Anybody else?
I can give the example if you want. So we're just going to take the classic example, map.mapg, and use that to map.f.g. Now we take f to be something more boring, like ID. We take g to be a function that adds 1 to any integer, except if that integer is 17, at which point it says error, holy heck, and then the program runs. Now, if you map g strictly, and then map f, right? Therefore, you are going to, or we're going to do it the other way. We're going to do g dot f. So now if you map f strictly and then map g, in the first version, all of f is going to happen, and we're all good, and then we'll sort of go through and do a fair amount of g and then a little bit of Sarah. Now if you do it the other way around, what's going to happen is, you're going to, because you're mapping them fused, you won't even get all the way to the first list before you hit this, error. I hit 17, and it's stored. So those sorts of properties, when you have laziness, sort of get carried for you automatically. And therefore, a lot more things preserve a lot more of the exact same meaning. Now, you might say, well, you don't care about these sorts of things. But if you do, laziness is what lets you get away with these things.
So laziness makes bad from twirl.
Sort of.
Because in Haskell, our data structures are our algorithms.